Okay, let's get started here. Let's get started. We started on fluorescence and let's keep going on the theory of fluorescence. And I introduced this the first few slides, the last class. And so let's go over that very quickly before we get to the major part of it. And so I think we should be going through most of this chapter, half of the chapter today. So remember, in this chapter, we are dealing with three things here. And so we are dealing with luminescence, molecular luminescence spectroscopy. And so there are three types of luminescence methods. So the three types of luminescence methods, as you see, okay, these are luminescence methods. And so what are they? Molecular fluorescence is a luminescence method, phosphorescence, and chemiluminescence. These are the three types of luminescence methods. Let's go into the details of these. And so in today's see here. Okay, so let's look at in each of these, the molecules of the analyte are excited. That's why they are called luminescence, coming from an excited state to a ground state. So in each of these, the analytes are excited. So when you hear of fluorescence, you have to look for excitation. So you have to look for the molecules in the excited state coming down to the ground state. In the same case, as you know, with phosphorescence, and the same is true of chemiluminescence, except, as you will see, there's a subtle difference between molecular fluorescence, phosphorescence, and chemiluminescence. So we use this for both qualitative and quantitative analysis. And collectively, this is what we call molecular luminescence. Now, the other thing we want to talk about is on fluorescence. Each one of you knows this. There's nothing new here, even when I present the Jablonski diagram, which we have gone over and over again and again. So you have in fluorescence, you must have the absorption of the photon, and that photon gets put into the excited state, as we have said, and it's a short-lived. I'm going to give you the time scale for fluorescence to complete this. So there is an absorption of the photon, and then once this is the photon is put in the excited state, at that point then it has to come down to the ground state. That photon has to emit that energy. And so that's what fluorescence is. Really, it is the emission of energy of a photon from the excited state to a ground state. And remember, we have just said here, it has to be from a singlet excited state to a singlet ground state. We all know that. On the other hand, phosphorescence, you notice here we have said fluorescence is short-lived. Phosphorescence is long-lived, as you know. It comes from a triplet excited state. So then that means it's longer, it's long-lived. The time scale of phosphorescence is much longer than for fluorescence. Notice there, in phosphorescence, you have to go from an excited triplet state. This is what we have emphasized again and again. Even when I when I look at your quizzes, I have to see it has to be from an excited triplet state. One has to mention a triplet state. Without that, it will not be phosphorescence. It has to be from an excited triplet state to a ground state. In both cases, Notice the similarities between fluorescence and phosphorescence. Both emit the photons. So energy is emitted. That's a similarity. Differences, one is from an excited state, that is fluorescence. The other one is from an excited singlet state. The other is from an excited triplet state. You notice the other difference is one is long-lived, the other one is short-lived. All right. So on the other hand, remember these are the three molecular fluorescence luminescence methods. Here, we are just comparing these very, very quickly before we just move into the details. Notice here, whereas fluorescence and phosphorescence entail an excitation source such that you must have absorption before you have fluorescence. You must have absorption before you have phosphorescence. When you have chemiluminescence, there is no excitation source. That's the difference, no excitation source. So there is an internal chemical reaction that provides energy to excite the molecule. Both of them entail, here is an internal reaction. It excites the photon. There is no excitation source. Now, you can see the similarity why these three methods are lumped together. There is an emission of energy. There's an emission of energy or a photon. All right? Everything comes from an excited state. But in chemiluminescence, no excitation source. And this usually occurs, you remember, for example, the fireflies, right? The fireflies in the evening, they have an internal mechanism through which a reaction occurs. And people study this all the time at any one given level in order for us to come up with devices that can internally produce energy. We study this nature, how nature does this. So these are the differences that we have talked about here. Right? In luminescence, in general, remember, fluorescence, luminescence, they are lumped together as luminescence. They are very highly sensitive. They are high sensitivity. And I'm glad we have done most of the experiments that we have done. You will see that fluorescence will do, today there's a group doing which one? GC and CV, right? There's a group that is going to do that. After that, we start on AA and fluorescence. That will be next week, okay? Unless there is anything, because we're having trouble with the AA for the first time, where we're trying to coordinate that. It can work, just like what the CV worried me so much, right? If we work. So I'm glad we have done all these experiments. They help us put together this information. So, in summary, what ties these three methods together? Luminescence, very high sensitivity. So if you have to choose a method that goes to very low trace amounts, all right, then you choose fluorescence, or you couple fluorescence with the method that you have. And so you're going to see. So they are very high sensitivity. There's a strong signal against a dark background. So that is important. See, the next thing I'm going to say here, look at what we have. Because of that, we use this like fluorescence. It is used in detectors for HPLC and CE, capillary electrophoresis. CE stands for capillary electrophoresis, and we use it for protein analysis and so forth. So this is why we have a detector. You realize on the JASCO HPLC, we have a detector there, which is a fluorescence detector, which I did not turn on, right? Did you realize it was just that? I just didn't turn it on. But if you play around with it long enough, and you're going to calculate the low levels, how low you can go in detecting a particular analyte, then you have to use fluorescence. especially if you're working with organic molecules, inorganic molecules, biological molecules, then you use fluorescence for detection. And that's why we have that particular fluorescence detector, and I'm glad it's there. Anyone who works with protein analysis or small analytes, and you use capillary electrophoresis in biological systems and just um, normal analysis, you're going to have capillary electrophoresis. It makes use of fluorescence. Even when you study proteomics, you know what proteomics is, study of proteins, all right? So you normally have a fluorescence detector. When you take your sample, for example, you have developed a gel and you put that gel and you scan it. Do you know what that is? You're using a fluorescence detector to see the proteins. So that's what I want to emphasize, that it has very high sensitivity. Okay? Let's move on. What's the theory of fluorescence? You all know this. I'm not going to belabor this. You know what this is, and we have talked about the theory of fluorescence, and I'm going to emphasize this again. Everybody knows all this information. There's nothing new here. The types of fluorescence. Now, let me mention here, because we mentioned it earlier, you might have forgotten about it. We have what we call resonance. The resonance, that means the emitted lambda is equal to it's the same as the excitation wavelength or lambda. And this is very occurs in atomic fluorescence. So we call that resonance. All right. Sometimes we say the emitted wavelength, all the light goes up, you emit the particular light or photons at a given wavelength, and then that amount of light, the same amount of light comes down to the ground state, is what we call sort of like Rayleigh scattering. Rayleigh scattering means all the amount of light that goes up to the excited state, all that amount comes down. All right? That's Rayleigh scattering, and we make use of that. We want the maximum amount of light. Types of fluorescence. One, we have resonance. The other one is stock shift. This is what I'm alluding to when we talked about this earlier. In stock shift, make sure you note this, because this is a typical conceptual question on what stock shift is. Notice that the emitted amount of light, the emitted lambda, emitted wavelength, is greater than the excitation wavelength. So here you have, normally we use Stokes shift. It has a higher intensity. It has a higher intensity. Okay, we use it for analysis in Raman spectroscopy. Right? So these are Stokes, and then we also have anti-Stokes. Anti-Stokes shift. You notice a shift when we talk about Raman scattering, we talk about a shift. The Rayleigh scattering at the center. I'm talking to myself here. So let me draw a picture here. So you have here, this is Rayleigh scattering here, and then you have another one that is a little bit lower in intensity. These two peaks, this one on one side should be higher than this other one. So both of them occur around the same distance. The middle here is what we call Rayleigh scattering. This is Rayleigh H scattering of light. And then you have here, this is the anti-Stokes. Stokes is a person who did this. Anti-Stokes. It is a little bit energetically, it is lower. It can be used for analysis, but we prefer to have a higher intensity for obvious reasons. So the opposite, this other one here, is the Stokes shift. So in stock shift is a higher intensity, and then we use it for analysis. So whenever they all occur on plus lambda, so this is, if it is plus, this is minus lambda. Sometimes I may amend this, but all I want to say is this plus here It's not absolute. It's telling you that on one side, it has the same wavelength as this other side. That's what I'm emphasizing here, okay? Later on, when I cover Raman spectroscopy, you will see what that means. Okay, let's go to the theory. I've mentioned these types of fluorescence. So let's now talk about this. Everybody recognizes this, I hope. I think everybody recognizes. Oh, what did I do here? Okay. So everybody recognizes this. And so if you recognize this, you notice there is here the ground state. You have two electrons for demonstration. This is the theory behind fluorescence, the theory behind phosphorescence. So the ground state, singlet state. Why is it called a singlet state? Sometimes you have two electrons paired, spin up plus a half, minus a half. The total spin is plus a half minus a half is 0. Spin multiplicity, as you all know, the spin multiplicity is simply given as 2s plus 1. So for the ground state here is 2 times 0 plus 1. This for this state, and that's why it's called a singlet. This is the singlet because the electrons are in one orbital, and remember, that's what happens. Here, notice here, if you excite them, you excite one of the electrons to an excited state, you leave one electron in the ground state, or they can all of them be in the excited state, excite both of them. And one of them has spin up, one of them has spin down. And so you have here plus half, that's minus. Let's make it clear it's a minus. So just conventionally, okay, this is minus a half, this is plus a half. Again, you notice therefore that the total spin in this state is S equals to half plus a half minus a half, which is 0, and therefore 2s plus 1 equals to 1. It's also a singlet state, as you can see. That's why it's called a singlet state. And this other one here, notice here again, if you excite both electrons, put them in an excited state, and all of them, they are in different orbitals. So you can say they can be molecular orbitals when we are dealing with molecules, and therefore they are in different orbitals. And you can see here, both of them have a spin up, and that means the total spin, considering these two electrons, will be plus a half and plus a half. That is 1, which means the 2s, spin multiplicity, 2s plus 1 equals 2 times 1, because it's plus a half plus another half plus 1, that is equals to 3. This is a triplet state. How is this related to the processes that we are talking about? You all know what that is. And so what we see is you have the electron spin, excited states. I've explained all this. So if you have an excited state, if it's paired, this is ground state. Now, if you have an excited paired state, that gives you a singlet. So a case like this one here, they are paired, but they're with opposite spins. And if those electrons, you notice there, that's why we call it a singlet excited state. And so it's going to lead to fluorescence from a singlet excited state to a singlet ground state. However, if they are unpaired, you can have these possibilities of the singlet state if they are unpaired. These are possibilities. So here, this is a ground state. You can have them, both of them paired. If they are paired together in an excited state, they give you a singlet state. If they are unpaired again, as the case here is, then they also give you a singlet state. All right? So these are the two options Remember, we talk about those vibrational states. The electrons can be paired or they can be unpaired. They can give you this singlet state. Now, what about if in this case, when they are unpaired, and notice they are unpaired, they have the, notice, if they are paired like this, that's a singlet state. This is another option for a singlet state, all right? Now, suppose they are unpaired, but they have spin ups and spin downs, spin ups. So what you're going to do, what you have here is a triplet state. So you have unpaired, excited state, but the electrons are unpaired, and then they have a triplet state in this case. Now it takes time for this to occur. It takes time to go to this state. It's more energetically demanding to go from a singlet state to a triplet state. Is energetically demanding. And that's why we said, let me go back here. This is why we say that phosphorescence is long-lived. It's a triplet state. It's long-lived because it takes time to change the spins, right? And so that is all this information you know. So that's the theory. You all know that theory. Nothing new here. There's nothing new under the sun at this point. Okay, now here next, what I'm going to do next is just go step by step in case we missed anything from our previous lecture on the Jablonski diagram. First, there are processes through this occurs, and we have deactivation processes. And the deactivation process is that process by which an excited molecule deactivation. It has energy, needs to lose that energy. So that process by which an excited molecule returns to the ground state. The excited molecule returns to the ground state. That means it gives up energy and falls down to the ground state, and that is deactivation. So this minimizing the lifetime of the electronic state is preferred. And so that is the activation. If it returns to the ground state rather than staying in the excited state, that's a preferred process. That's what molecules prefer. And that is what causes, let's say, stability of molecules in chemical reactions, stability of molecules in living systems. They prefer to be at the ground state. If there is no ground state, then we are talking about the disease state. Okay? Those are the kind of things that you have to think about. And therefore, in a deactivation process, that time scale, we need it to be faster, and we can calculate the rate constant. A faster rate constant is preferred. A rate constant, the faster rate constant will predominate if it's faster. So, and people spend all their time doing this, calculating those rate constants. And that's why people design probes for this kind of reactions. So then there is what we have here, a deactivation process, radiation-less deactivation. You know, class, what I'm talking about is this. This is the Jablonski diagram. How about? That's what I'm going over. There's nothing you don't know here. So let's say, for example, this is the famous Jablonski diagram. You know, you have here the ground state, singlet state, associated with lambda. If those, remember, we only use 2 electrons for illustration. There are many processes that occur. We just use 2 to help us understand the process that is occurring. So we have here the ground state, which can be singlet state, S naught, ground state, singlet state. Electrons then can be excited either by family or whatever process. Usually we use energy. And we have introduced one other process by saying sometimes this can be an internal when there is a chemical reaction. All right? So we have a ground state, singlet ground state. Then that is absorption, you all know. Then we can have various lambdas corresponding to the amount of energies. As you notice here, lambda 2, lambda 1, lambda prime here. So again, those are very nice diagrams to illustrate this. But you have to understand at this point that we are only picking up few processes to enable us understand what is happening in molecular systems. And so here, then you can go to the vibrational states. You can see at the ground state, you have various vibrational states. And these electrons, if they are from the excited singlet state, and you can see the vibrational, it relaxes and gives up the energy. You do not fully understand how that happens. That is continuous investigation. So all those, you see, those are singlet excited states. Then we have singlet ground states here as naught. And then you see here when these electrons come to the ground state, and you have had me say molecules. At the molecular level, we are dealing with the electrons. It's electron transitions that are occurring. So the molecules come to the ground state. What is happening? They are releasing energy. What is happening? It's electrons that are involved. And so that's what is happening here. This is what I'm talking about. You can see what internal conversion means. Internal conversion, you can have overlapping of this singlet state. You can see that is internal conversion within the overlapping singlet states. And then you can see here vibrational relaxation. Vibrational relaxation can occur in the excited state or even at the ground state. All right? So that is what I'm talking about. This is what I'm talking about. Deactivation, the loss of energy to come to the ground state. We have radiation-less deactivation. So we do not understand this. Some of these processes just means that, for example, in this, some of these processes that occur here, we know energy is involved. Energy is involved. But sometimes we don't see that amount of energy. And people strive to measure this amount of energy. This is what we are trying to understand. That's why we call it radiationless. All right? This picture here perhaps summarizes everything else that you need to know about the Jablonski diagram. Look at it. Number one, we have vibrational relaxation. The molecule can give off some of its energy from the absorbed light. Usually, UV light by jumping to a lower energy vibrational state. The excess energy is used to make the conversion because there is no light given off. That is as much as we know. Because that amount of energy that is given off from one electron to another enables that process to occur, but no energy, no light is given off. We have internal conversion. The molecule transitions to a lower energy electronic state without also giving off energy. It's between those states. The excess energy is used to convert the molecule from one electronic state to another. So this is poorly understood how that happens. But we know it happens. Evidence, scientific intelligence, that happens. Then we have the external conversion. The external conversion is associated with going from a singlet state to a triplet state. So it takes energy and time to go from that state to that one. So this is a triplet state now. Like we know what the triplet state, what that involves. It is what we call now phosphorescence. Is again changing from a triplet state, or when molecules or electrons give off the energy and change their state, the spin state, from a triplet state to a ground state. That is phosphorescence. You have to invoke the triplet state and the singlet state. Otherwise, it will not be phosphorescence. And why is that important? You notice, for you to go from a singlet state to a triplet state and a singlet state, that involves a little bit longer energy. That's why we say phosphorescence is long-lived. is going to involve. It's longer. It occurs at a longer wavelength. You can see here lambda number 4, lambda 4, as you see. Okay, so that summarizes this. We have internal conversion. Molecule gives off energy to an external source, such as by collisions, because in order for the electron to change spin state, they have to collide. That can only be made possible by such a process. So a molecule can collide with each other and therefore change the configuration or the state of the electrons. So the molecule can collide with each other, or if it's within a solvent system. And when you talk about solvent systems, I really need people to understand this, class. Solvent systems occur all over in our bodies and so forth. You learn about these long processes in biological systems, don't you? Solvent systems. What is a major solvent system? In test tubes, in vitro systems, then you will see that you have one kind of solvent. Even in our body system, you have methanol sometimes occurring. So that is what's going to cause this. Sometimes when these molecules collide or solvents, this is what we call quenching. We call that quenching. Okay, because it lowers the energy. And then we have intersystem crossing. Molecules goes from a singlet to a triplet excited state, and it uses up energy to change the spin of an electron. That summarizes it. So next then, again, I go step by step here. Notice these are the terms from the energy level diagram, which we have seen, Jablonski diagram. You understand this, nothing new. So these are the terms. Absorption, the effect of absorption is to excite. I like this particular slide because it summarizes very succinctly what we need to understand. The effect of absorption is associated with the excitation of an electron from a singlet state to another singlet state. Then the process, here is where now I give you the time, the lifetimes. So for absorption, the analyte molecules absorb the photon. It's a very fast process. Notice the time scale, 10 to the minus 14 to 10 to the minus 15 seconds. If you can remember that time scale, that will be better, because then it gives you the tangible time that you know. So the electron is promoted to a higher energy state. It seems slightly different wavelengths are involved, and it can go into different vibrational energy levels. Now, here's the term, vibrational relaxation. It is associated with deactivation. You know, in the Jablonski diagram, if you look back, this is the Jablonski diagram. You have vibrational relaxation. You can see this time here, and you can also see them here. So, and you can see it is associated with changing from one vibrational energy level to another, as you can see. And so it is, those are the terms in summary that we're talking about here. Vibrational relaxation, the effect is to deactivate, to lose the energy. And we know it is radiationless. They occur within the vibrational states. And how is that? The molecules collide with each other. There's loss of excess vibrational energy and relaxation to lower vibrational levels within that excited electronic state. Next, we talk about internal conversion. So again, the process is associated with deactivation of a molecule or electrons. And this, you understand what that means. The molecule passes to a lower energy state. The vibrational energy levels of the two electronic states would overlap in order for you to have internal conversion, and the molecule passes from one electronic state to the other. Now, the other term is fluorescence, which we understand again. The fluorescence, we know. The loss of energy, that is also with the deactivation. The effect of that is the emission of energy, H nu. Okay, then the process, notice the process. We said fluorescence is, notice which one is longer. So the emission of a photon via a singlet to a singlet through a singlet transition, it is short-lived, but the excite is short-lived. This is the time scale of fluorescence. 10 to the minus 9 to 10 to the minus 7 to 10 to the minus 9 seconds. So that means fluorescence is long-lived, all right? It occurs at a longer wavelength than absorption. Do you realize that? Fluorescence occurs at a longer wavelength because of the time scale. In other words, we are emphasizing the same fact. You must have absorption before you have fluorescence. Is that not the case? That's why we have these time scales. For fluorescence, 10 to the minus 7, 10 to the minus 9 seconds. For absorption, what's the time scale for absorption? I've given you a number. 10 to the minus 14, 10 to the minus 15. So that is shorter. And then you put the electrons or the molecules in the excited state, and then they have to come down to the ground state. So that's what we are talking about. Let's talk about the other process, intersystem crossing. The effect of that is deactivation again. You notice the term deactivation throughout, loss of energy, it's radiationless, and this intersystem crossing, it goes from a singlet state to a triplet state. So you can look back through your, go through the Jablonski diagram and make sure you know this. So intersystem crossing from a singlet excited state to a triplet excited state, there's that change, the electron changes spin. And that means it's going to take a little bit more energy. And therefore, intersystem crossing, the spin of the electron is reversed. It leads from a singlet to a triplet state. And it occurs more readily. When does this occur? This, I'm going to give you a question later. And later we're going to have, in the final exam, you're going to rate some of these processes. You're going to tell me which molecules or which particular system, if I give you a structure, which system will favor phosphorescence. Let's get this right from the beginning. Phosphorescence occurs more readily if the vibrational levels of the two states, they overlap. When is that possible? You have to look for these heavy atoms. The common molecules with heavy atoms, such as iodine, bromine, if you see a bromine and an iodine, those heavy atoms are going to encourage intersystem crossing processes. All right? That's what you have to look for. Okay? The other term is external conversion. Again, look at the Jablonski diagram. Make sure you fix this in your mind. And when I've tested you many times, many of you have gotten this right. And so I'm confident you can do this very well. So in external conversion, the effect is a deactivation, radiationless. Let's flash back while we are here. So you notice again, going to Jablonski diagram. So you have here internal and external conversion. So you have internal conversion. You have internal conversion when the singlet states overlap, right? You have internal conversion. You can see here from a triplet state to a singlet state, or from a singlet excited state to a singlet ground state. So that is internal conversion, and we have external conversion here as well. Okay. Now, let's look at fluorescence now. Again, fluorescence, the effect, deactivation again, loss of energy, emission of light, H nu. So the emission of a photon via singlet to a singlet transition state, short-lived, as we have said. We've talked about here, let me see, external conversion. We've talked about the external conversion, and let's notice there, I have put that in red. You know, there are things I think about. When I put it in red, it means that's so important for people to notice. That's when I say, okay, this is important. Okay, the effect is deactivation. There's the emission of light. But look, what is the lifetime? We all know the process. It is the emission of a photon from a triplet excited state to a singlet ground state. Because of that change in the spin state, it takes longer. Notice the timeline of phosphorescence. It's 10 to the minus 4 to 10 to 1 to 10 seconds. 10 to the minus 4 is how many milliseconds?
0.1.
0.1. So all the way from 0.1 to how many milliseconds? 10,000? So you can count it later. So usually if I count here, I walk my steps. 1 step is 1 second. You don't know. I found that to be true. I can count my clock. If I step 1, 2, 3, 4, 5, I know I'm counting seconds. So if you're counting up to 10, so you can observe it. You can actually see it. How can you do it? Lower the temperature. Then you can see it. So that is how phosphorescence is. 10 to the minus 4. It is in the millisecond time scale. Okay. Now that I've said, I've made it clear. We have reminded ourselves on this. I'm going to talk about a fluorescence quantum yield. So what is it? Let me define it before I give you these terms here that go into it. Phi, F, some people call it phi, right? I call it phi. You know, phi. That's phi, right? So that's what we call phi. F for fluorescence. So we're talking about fluorescence quantum yield. We also have a quantum yield for phosphorescence. I will not touch on that. And I have a book of photochemistry in my office. It has numbers for molecules. So if I'm doing an experiment, sometimes I want to do a comparative, make a comparison in order to come up with the correct number. I just pull it up, all right? So when we do fluorescence, I've been thinking, should I get you involved in quantum yield? They say yes, no. Well, I'm debating on it. Remember when I gave the talk, the guideline, I said maybe not. Okay. So a quantum yield is, I'm going to define it right away before I go into this. A quantum yield simply means it's a ratio of the molecule in the excited state over the ratio of the molecules in the ground state. That's what a quantum yield is. That's what you're measuring. It's a measure of the number of photons. I'm going ahead. I'll come back to it. But let me give you this. Yep. Right here, the quantum yield phi. If you step ahead, you will see it is the total number of luminescing molecules. Those are molecules in the excited state over the total number of excited molecules. And then that formula that I put earlier comes up. Let's go back. So if you have all the molecules in the excited state coming down to the ground state, you have a quantum yield of 1. All right? And molecules like this, we use them. Okay. All right. See, what does it consist of? You know, we've talked about this. If you think about it, the molecules in the excited state, some of them can change spin. if it's a molecule, sometimes you can break it up, right? So that's what this is all about. You have, it is made up of K sub F, that's a fluorescence, rate constant for fluorescence, K, and then you have KEC, the external conversion. So all these at the denominator are all the processes that we have talked about in order for a molecule or electrons to come to the excited state. What is it made up of? It's made up of the rate constant for the external conversion, it's made up of rate constant for internal conversion, and the system crossing, it can occur. So that is what it is. And you can see all these things that we have talked about. For an external conversion, singlet excited state to a singlet ground state, or for internal conversion, you have a singlet excited state to a singlet ground state. Intersystem crossing, singlet excited state to a triplet state, or pre-dissociation. Some molecules can break up. You can measure that, or some molecules can come together. They can associate. That's why we do these processes in very dilute solutions to prevent that occurrence. So you don't have to memorize the formula. No. I'm not testing you on that. We're together. Just understand that those processes that we've talked about come into play. There are rate constants. You can determine those rate constants, the Ks for each one of them. We can do that very well. Now, we have already talked about this. This is a repeat. Vibrational relaxation is much faster than fluorescence. Okay? Here is the point I emphasized. Fluorescence occurs at wavelengths longer than the absorbed radiation, except where no vibrational relaxation can take place. This is why we have those lambda prime relaxation and lambda relaxation. And the resonance fluorescence, the wavelength at which energy is observed is equal to the wavelength that photons are emitted. Predisposition is a result of internal conversion, and electron moves to upper vibrational levels to a lower one, and it can cause bond rupture. That's why it's called predisposition. All right, intersystem crossing. Now, we gave this for intersystem crossing, chlorine, iodine. That's if they are in a solution, that's what we call the heavy atom effect. Others, like oxygen or other paramagnetic systems, cause intersystem crossing. Now, I'm going to leave it here for today. I want you to notice that there is quinine. If you have a structure of quinine, I would finish this in the next class on Wednesday, this chapter. That is my hope. All right? Okay, have a good day.